Okay, diving right in today, we're looking at a really interesting area, how to build AI. Language models specifically that are not only powerful, but, super efficient too.
And it all starts with, well, a challenge. That's how this paper kicks off, actually.
Bang out the problem.
Exactly. Like, how do we deal with these massive amounts of text data that we're throwing at these AI models?
Because they're getting bigger and bigger, right?
Right. And the problem is, well, the old way of doing things, especially with these transformer models, they eat up way too much computing power and memory when you start giving them really long pieces of text.
I imagine trying to run, I don't know, the entire Library of Congress through your old laptop, right?
Yeah.
And just choke.
Yeah, basically. And that's where this new model, RWKV-7, which they've nicknamed Goose, by the way.
Goose. I like it.
Yeah, it's kind of catchy. Anyway, this model comes in as a potential solution. It's part of this bigger trend of moving towards a different type of neural network architecture called RNN, recurrent neural networks.
And the key with these RNNs is that they're supposed to be much better at handling these long sequences of information.
Yeah, because they have these things called compressive states, which is a fancy way of saying they can process information in a way that doesn't require their memory and computational needs to explode as the text gets longer.
Okay, so instead of needing like a whole server farm to run these things, you could theoretically run them on something much smaller.
Potentially, yeah. That's the hope. It's all about finding a balance, right, between power and efficiency. And one of the key ideas here is, and this is a big difference from how transformers work, is that the computational cost of this new model, it grows linearly with the length of the text. So it's a much gentler increase.
Okay, so like a steady ramp up instead of this sudden exponential spike.
Exactly. And that's compared to the quadratic scaling of the transformer's attention mechanism. It's a much steeper increase in resource usage.
And, when you think about it, this idea of efficiency, it's becoming more and more crucial in AI because, well, the models are only getting bigger and the data sets are getting more massive.
Right. It's not sustainable to just keep throwing more and more computing power at the problem. We need smarter solutions.
We need more geese, maybe?
Maybe, yeah. More efficient geese. And what's really neat is that this RWKV-7, it's designed to be trained in a very parallel manner, which means, well, it can take full advantage of the kind of hardware we have now with multiple processors working together.
So it's efficient not only in how it runs, but also in how it learns.
Exactly. It's efficient throughout the whole process. And it's not like they just pulled this idea out of thin air. It's based on this concept called the Delta Rule, which comes from the field of online learning.
Online learning. For those who, might not be familiar, it's this idea of a model constantly learning and adapting as it encounters new information. Sort of like how we humans learn.
Right. Yeah, exactly. It's a more continuous and dynamic way of learning as opposed to, say, batch learning, where you train a model on a huge chunk of data all at once. And the core idea behind the Delta Rule is it's about how the model's internal state, it's like its memory, is updated.
So instead of just completely wiping the slate clean every time it learns something new.
Right. Instead of completely replacing the old information, the Delta Rule says, let's keep some of that old stuff and just sort of tweak it based on the new stuff we're seeing.
Kind of like revising a document instead of starting a whole new one from scratch.
Yeah, a very apt analogy. And this makes it much more efficient, right? You don't have to relearn everything from scratch every time. And this RWKV-7, it takes this fundamental Delta Rule idea and really runs with it.
It evolves it, so to speak.
Precisely. They even call it expressive dynamic state evolution in the paper. And it's all about how this model's internal memory, or state, changes and adapts over time as it's processing a sequence of information.
And one of the key changes here, compared to earlier versions of RWKV, like, what was it? RWKV-6.
RWKV-6, yeah.
They've shifted from this diagonal transition matrix to something they call the extended delta rule. I know that sounds a bit jargony, so break that down for us a bit.
Sure. So you can think of the model's state, its memory, as being made up of lots of different components, sort of like different channels of information, right? And in the older versions, these channels, they might have updated in a more interconnected way. The extended delta rule allows for a more fine-grained approach. The amount of each channel that gets updated can actually depend on the specific data that's being processed, and crucially, each channel can update independently.
So it's like each part of the memory is kind of doing its own thing based on what it's seeing.
Yeah, that's a good way to put it. And The authors of the paper, they argue that this makes the model much more flexible and capable of understanding complex relationships in the data.
Because it's not just blindly updating everything at once, it's being much more selective and strategic.
Exactly. Now, on top of this, and this is where it gets really interesting from a theoretical standpoint, they're claiming that RWKV-7 has this expressive power that goes beyond a certain complexity class called TC0. And this is kind of a big deal because, well, a lot of the current architectures, including transformers, they seem to fall within this TC0 class.
So what you're saying is that RWKV-7 is not just doing the same things faster, it might actually be capable of things that other models just can't do.
That's what they're suggesting, yeah. And they even make this analogy of RWKV-7 having an internal scratch pad where it can sort of manipulate information in a more complex way than these TC0 limited models.
Like it's actually, I don't know, doing some calculations or something.
Right. It's not just memorizing and recalling, it's actually processing the information at a deeper level. And to back this up, they have this theoretical proof that RWKV-7 can recognize all regular languages, which are like these fundamental building blocks of computation, using a fixed number of layers.
So no matter how complex the language gets, it can still handle it efficiently.
Yeah, and this ability is tied to a specific operation that it can perform called copy, which, interestingly enough, wasn't present in the original Delta rule.
So it's like they've taken this basic idea and added this new capability that gives it this whole new level of power.
And it's not just the state evolution that's been updated. They've made a bunch of other architectural tweaks compared to RWKV-6, the previous version.
They've refined the Goose.
Yeah, exactly. For example, they simplified this thing called the token shift module.
Okay, now remind me, what does the token shift module do again?
So it's this mechanism that helps the model learn patterns within a single layer. It does this by performing a kind of short 1D convolution. It's a bit technical, but basically it's looking for patterns in a very localized way.
Okay, got it.
And in RWKV-6, this token shift, it was data dependent, which means it would change depending on the specific data it was seeing. But they decided to go back to a simpler approach, similar to what they used in, I think it was RWKV-4 and RWKV-5.
Back to basic.
Right. And the reason for this change was all about speed, both in terms of how fast you can train the model and how quickly it can process new information.
Makes sense. Sometimes simpler is better.
Especially when you're dealing with AI, where efficiency is key. And they also removed this thing called receptance gating in the channel mixing module. Again, this was all about speeding things up.
So streamlining the architecture.
Yeah, making it leaner and meaner. And they've also increased their use of these things called low-rank projections. These are kind of like a way of compressing the information the model is working with.
Like creating a summary of a long document that still captures the key points.
Precisely. And this helps reduce the overall size of the model, which again is good for efficiency. It's this constant balancing act in AI, trying to get the best performance with the smallest, most efficient model possible.
Always trying to find the sweet spot.
Exactly. Now, another interesting change they made was to the way information decays in the state over time.
Decay. What do you mean by that?
So as the model processes information, it needs a way to sort of forget old information and make room for new information, right?
Like our own brains, we can't remember everything forever.
Exactly. And this decay mechanism controls how quickly the model forgets. They made some adjustments to this to make the training process more stable and hopefully improve the overall accuracy.
So it's about making sure the model is letting go of the right information at the right time.
Precisely. And on top of that, they've also introduced this thing called value residual learning.
Now that sounds interesting. What is that all about?
So it's this idea where the model actually takes information from the very first stage of processing, and it sort of blends it with the information at the current stage. And this technique has been shown to improve language modeling performance in other research.
It's like adding a little bit of the original context back into the mix.
Yeah, to give it a more holistic understanding of the information. Now, all of this, the architecture, the state evolution, the copy operation, it all needs to be trained on a lot of data.
You can't have a smart AI without feeding it a lot of information.
Exactly. And for this, they've created this massive new data set called RWKV World v3.
Tell us about this data set. What's in it? How big is it?
Well, it's really huge. We're talking about 3.1 trillion tokens of data.
Trillion with a T.
With a T. It's all publicly available data, and it's multilingual, covering English, other languages, and code. It's their attempt to catch up data-wise with some of the really big players out there who are training on, like, 15 to 18 trillion tokens.
Wow, that's a data feast.
It is, and they've tried to keep a good mix of content in there, similar to their previous data sets, web content, books, code, all sorts of stuff. But they did add a bit more Chinese novels this time around.
Okay, interesting. So it's got this new architecture, this massive data set. And what's great is that they're actually releasing pre-trained models based on all of this, right?
Yeah, that's one of the great things about this research. They released 4 pre-trained RWKV-7 World v3 models. They range in size from, 0.19 billion to 2.9 billion parameters. And they were trained on a ton of data, between 1.6 and 5.6 trillion tokens.
And these are available for anyone to use?
Yeah, they're on Hugging Face. All the model weights and details about the dataset are there. And the code for training and using the model is on GitHub, all under an open source license.
That's great for transparency and for moving the field forward.
Absolutely. It lets anyone replicate the results or build upon their work. So that's the setup, right? The architecture, the data. Now the big question is, how well does it actually perform?
Yeah, does it live up to the hype? Put up or shut up time.
Well, they did a bunch of benchmark testing, as you'd expect. They used standard language modeling benchmarks, both for English and for multiple languages. They used this tool called the LM evaluation harness to do it all. And they compared their results to other open source models that are in a similar size range, similar number of parameters.
So apples to apples, basically.
Exactly. And one of the big findings, and this is what they highlight in the paper, is that they see this really significant improvement in the multilingual benchmarks, especially when you look at the trade-off between computational cost and accuracy. They even call it a dramatic Pareto improvement compared to transformer models.
So better performance with less computational effort.
Right, especially for languages other than English. Now, on the English benchmarks, they got comparable results to the transformer models, but importantly, they used significantly fewer FLOPs. FLOPs, that's floating point operations per second. It's a measure of how much computation is being done.
So again, doing more with less.
Exactly. Now, one thing to keep in mind is that they weren't able to train these models completely from scratch. Because of resource limitations, they had to start from pre-trained checkpoints of earlier versions of RWKV. And they speculate that if they had been able to train from scratch, the results might have been even better.
Okay, so there's still room for improvement, potentially, but the results are already quite impressive.
Right. Now, to address concerns about data leakage, the idea that the models might have already seen some of the benchmark data during training, they also did an evaluation on completely new data.
Data that the models could not have possibly encountered before.
Exactly. This is really important for seeing how well a model can generalize to truly new information. For this, they collected a bunch of recent research papers from RWKV, focusing on computer science and physics, and they also grabbed some fresh open source code from GitHub.
So stuff that was created after the models were already trained.
Right, all created after January 2025. And what they did was they tested how well RWKV-7 and other leading models could compress this new data.
And why is compression a good test for this?
Well, the idea is that if a model can compress data well, it means it's able to understand and represent that data efficiently. It's like if you can summarize a long document concisely, it means you've understood the key points.
Makes sense. So how did RWKV-7 stack up on this new data compression test?
The paper has a table that shows the compression rates achieved by different models on this new data. And it's interesting to see how they compare. It gives you a sense of how well each model can generalize to information it's never seen before.
So it's a more realistic test of their true learning capabilities.
Exactly. Now, they also looked at how well RWKV-7 could recall information. They used this task called multi-query associative recall, or MQAR. It's a way of testing the model's memory, essentially.
Can it remember things it's seen before, even in a long sequence of information?
Right. And it turns out that RWKV-7 did pretty well on this task. Even though they acknowledged that training for MQAR can be a bit tricky and unstable, they still found that the model was able to recall key-value pairs even when dealing with really long sequences.
So it's not just processing information on the fly, it's also retaining some of that information for later.
Which is crucial for any kind of complex task. Now, another interesting benchmark they used was this thing called the Mechanistic Architecture Design Benchmark, or MEA for short. It's basically a suite of specifically designed tasks that are meant to test very fundamental sequence modeling abilities.
So kind of like testing the basic building blocks of how the model handles sequences.
Yeah, exactly. Things like being able to copy sequences, reverse them, perform simple operations. And they tested RWKV-7 on this benchmark alongside other models like transformers, Mamba, Delta net, it gives you a good comparison of how they all stack up on these core abilities.
And where did RWKV-7 fall in all this? Was it a star performer, middle of the pack?
Well, the results are all laid out in the paper. There are tables and figures that show how it performed on each of these tasks compared to the other models. It's really interesting to dig into if you want to see where it shines and where it might have some weaknesses.
So, no model is perfect, but this gives you a sense of its strengths and weaknesses.
Right. Now, remember, one of the big motivations behind developing RWKV was this idea of handling really long sequences efficiently. And to really test that, they did a bunch of experiments with something called passkey retrieval.
Okay, explain passkey retrieval. What's that all about?
So imagine you have this really long piece of text, and hidden somewhere in there is this specific key phrase. The model's job is to find and retrieve this key. And the trick is the surrounding text can be very long and full of distractions. They might use repeating sentences or just a lot of irrelevant information to make it harder.
So it's like finding a needle in a haystack, but the haystack is a whole library.
Yeah, exactly. And they found that RWKV-7 did remarkably well on this. The larger model, the 2.9 billion parameter one, was able to successfully retrieve the key even in contexts up to 35,000 tokens long.
That's a lot of text to sift through.
It is. And they even found that if they fine-tuned the model on even longer sequences, up to 128,000 tokens, they could improve its performance even further.
So it's showing that it can really handle those massive amounts of information.
Yeah, which opens up a lot of possibilities for things like document summarization, question answering, all sorts of things where you need to process and understand large amounts of text.
Now, they also briefly mentioned something about state tracking using group multiplication tasks. What was that all about?
So these group multiplication tasks are a way to test how well a model can keep track of its internal state, its memory, as it processes a sequence of operations. It's like, can it remember what it's done before and update its memory accordingly?
And how did RWKV-7 do on this?
Well, they found that it was better at state tracking than Transformers, Mamba, and S4, although it wasn't quite as good as classical RNNs on this particular type of task.
So it's striking a decent balance there.
Yeah, it seems to have good memory capabilities, but there's maybe some room for improvement. Interestingly, this finding kind of ties in with their earlier point about RWKV-7 being able to recognize all regular languages. It suggests that the way it handles its state, its memory, is fundamentally connected to its ability to process sequences effectively.
So all these different pieces are starting to fit together.
Exactly. Now let's get down to the nitty-gritty, speed and memory usage. These are really crucial factors for any AI model, especially if you're thinking about real-world applications.
Right, because if it's too slow or it takes up too much memory, it's not going to be very practical.
Exactly. So they compared the core computation of RWKV-7 with that of RWKV-6, its predecessor, and also with Flash Attention v3, which is a highly optimized version of the transformer attention mechanism. They have two versions of the core computation, a faster one that uses lower numerical precision called bfloat16, and a more precise one that uses FP32. For these RWKV-7 World models, they use the more precise FP32 version.
So how did it perform? Was it noticeably faster?
Well, they found that the forward pass, which is the part of the computation that happens when the model is processing information, is much faster than the backward pass, which is used during training. And for inference, which is just using the trained model, it's even faster because you don't need to store as much information.
So it's quick on its feet, so to speak.
Yeah. They also provided some formulas for estimating how much memory you'd need during training for different architectures, and their actual measurements were pretty close to those estimates.
So, you can actually plan ahead and figure out how much computing power you'll need.
Right, which is really important for researchers and anyone who wants to use these models. Now, to really show how versatile this RWKV-7 architecture is, they also built a multimodal version of it called Visual RWKV-7.
Multimodal meaning it can handle more than just text.
Exactly. They combined RWKV-7 with some advanced vision models like SIGLIP, DynoV2, and SAM. These are systems that are really good at understanding images.
So it's like giving the model eyes.
Yeah, essentially. And they tested this visual RWKV-7 on a bunch of tasks that involve understanding both images and text, like visual question answering. And it got really good results, showing that this core RWKV-7 architecture has potential beyond just language processing.
So it's a flexible, multi-talented goose.
You could say that, but of course no research is without its limitations. The authors are very upfront about that.
What were some of the key limitations they identified that we should be aware of?
Well, one thing they pointed out is that the performance of some of the core computations can be sensitive to the numerical precision used in the implementation. What that means is that if you're not careful with how you implement it, you might not get the full performance benefits.
So careful engineering is required.
Definitely. They also noticed some differences in training behavior depending on which version of the core computation they use. Another practical limitation was the amount of computing power they had available for training. They were using 96 NVIDIA H800 GPUs, which is a lot, but some of the really big models out there are trained on much more than that. And this meant they had to train from existing checkpoints, which might have limited the final performance.
So it'd be interesting to see what they could achieve with even more resources.
Yeah, absolutely. Now, in terms of future work, there are a lot of exciting directions. One obvious one is training even bigger models on even more data, scaling things up.
Bigger Goose, bigger data, bigger result.
Maybe, yeah. They're also very interested in exploring ways to make the models faster. They mentioned things like dual pipelining, mixture of experts, multi-token prediction, FP8 training. These are all techniques that have been used in other models to improve speed and efficiency, and they also want to optimize the core computations themselves, make them even more efficient. Plus, they're looking into distributed training, which is how you train these really big models across many different computers. It's a huge engineering challenge.
It sounds like they have a lot on their plate.
They do, yeah. They're also really intrigued by the idea of using RWKV-7 for this thing called chain of thought reasoning. It's where the model actually shows its thought process, step by step, as it's solving a problem.
So it's not just a black box. You can actually see how it's thinking.
Exactly, which could be really useful for understanding how these models work and for building trust in their outputs. Now, one final interesting thing they discovered was this sensitivity to the initial token.
The initial token, what do you mean?
So when they were testing the model on this benchmark called Lambda, they found that the model's performance could actually be affected by whether or not they included this special token, end of text, at the very beginning of the input.
Okay, that's a bit strange.
Yeah, it was unexpected. Their analysis suggests that the model might sometimes have trouble holding on to that very first piece of information throughout the whole process. So they recommend always including this token at the beginning of any prompts you give the model. They even suggest a specific format for chat applications to make sure it works optimally.
So it's a little quirk to be aware of.
Exactly.
Yeah.
So, to wrap things up, what have we learned about RWKV-7?
We've seen that it's a really promising new architecture for building efficient language models.
Yeah.
It's got this innovative way of handling its memory, this expressive dynamic state evolution, as they call it. And it's got some theoretical advantages, potentially even being able to do things that other models can't. Plus, it performs really well on a bunch of benchmarks, especially in multilingual settings and when dealing with long sequences of information. And the fact that they're open sourcing everything is fantastic for the field.
And for you, our listener, who loves to learn new things quickly and deeply, the idea that we might have a model that can process tons of information without needing huge amounts of computing power is super exciting, right? Imagine being able to analyze massive documents, have really in-depth conversations with an AI, all without needing a supercomputer. The potential is huge.
Yeah, and the fact that it's achieving these results with fewer resources is also really significant, given how much energy and resources AI development is currently consuming. It points towards a more sustainable future for AI.
And there are so many interesting questions that still need to be answered. How will it perform on even more complex real-world tasks? What will the practical implications of its theoretical advantages be? How can we make it even faster and more stable? It's a wide open field.
And the fact that they've made their work so accessible means that anyone can potentially contribute to answering those questions.
Exactly. So here's a final thought to leave you with. We've talked about how RWKV-7 has this dynamic memory, how it can constantly update and adapt its internal state. Unlike transformers, which have a more static memory mechanism, this makes you wonder, could this kind of architecture lead to AI systems that are more, fluid in their thinking?
Mm-hmm.
Could we see AI that can truly reason and manipulate information over long periods of time, not just memorize patterns?
It's a tantalizing possibility. And with that, we'll wrap up this deep dive into RWKV-7 Goose. Thanks for joining us.